Hello, welcome to today's lecture in Quantitative Methods on correlations. We're going to go through multiple different sections today. The first topic is on seeking correlations and identifying what correlations are. So a correlation exists between two variables when higher values of one variable consistently go with higher values of another variable, or when a higher value of one variable consistently go with lower values of another variable. So when one goes up, the other one goes up, or when one goes up, the other one goes down, and that we consistently see this pattern. So a few examples to make it a little bit more clear. There's a correlation between the variables amount of smoking and likelihood of lung cancer. That is, heavier smokers are more likely to get lung cancer. So as smoking goes up, the probability of getting lung cancer also goes up. There's a correlation between the variables height and weight for people. That is, taller people tend to weigh more than shorter people. And there's a correlation between the variables demand for apples and price of apples. That is, demand for apples tends to decrease as price increases. So people are less likely to buy more apples when the prices are high. How do we display correlations? Well, we use scatter diagrams or scatterplots. And this is a graph in which each point represents the values of two variables. And so this is a really good way of seeing if there are correlations. So let's take a look at an example of how we can create a scatter plot. And here we're going to be using a data set on prices and characteristics of 23 diamonds from gem dealers. And so we have a list of different diamonds, the price, weight, and then depth table, color, and clarity. And so we're going to take a little look at the price, carat, color, and clarity potentially, which are usually key variables that we look at when describing diamonds. And so here's a scatter plot that was created for weight, which is expressed in terms of carats when we're talking about diamonds, and price in dollars. And so this is an example of a scatter plot, and it's showing here we can see whether there's a relationship or a correlation between these two different variables, right? And so here, for example, diamond 10, we see has a weight of 1.1 carats, or 1.11 carats, and a price of $3,670. And so that's where it's located over here. Diamond 16 is about 1.5 carats and a little less than 8,000. Looks like about $7,500. And so by putting each of the different points onto a graph, we can see, okay, it looks more or less like as the weight goes up, so too does the price. We see they seem to go up together. So how can we create this type of scatter plot? Well, we assign one variable to each axis, right? So on the x-axis before we had the weight, and on the y-axis we had the price. And so we label the axis so that people know what's on it. And we put the length of the axis or the units on the axis far enough that it fits all the data comfortably, right? So if price goes up to about 15,000, then obviously you would want to go up to at least 15,000. You'd want to go a little bit past so that your last point's not right on the edge. Something like 16,000 would be good. You don't want to go too far. You won't want to go, if your last value is $15,000, you won't want to go up to 50,000 because then all your points will be condensed in. So you want to, choose far enough that all your data fits comfortably into the graph. Now, sometimes the axis selection is arbitrary. It doesn't matter whether you put, one variable on the x-axis or on the y-axis. But usually or often, we tend to make decisions based on whether we think one variable depends on the other. And usually, if we think that one depends on the other, we put the one that we think the explanatory variable, so the one that we think does the explaining, on the horizontal axis, and the response variable, or the explained variable, on the vertical axis, right? So in this case, we expect that the price of diamonds will depend on the weight. It's not that weight of diamonds is affected by price. And so because we expect that price is dependent on weight or is partially explained by weight, we would put weight on the x-axis or the horizontal axis, and we'd put price on the vertical axis or the y-axis. So we choose a range for, in this case, for fitting the axis. So we chose a range of 0 to 2.5 carats for the weight, and $0 to $16,000 for the price axis, which we saw in the figure that we looked at. For each diamond that were in the table, we plot a single point at the horizontal position corresponding to its weight and the vertical position corresponding to its price, right? So if its weight was 1.11, we'd go out to 1.11 horizontally, and then we'd 1.11 horizontally, and then if its price was $3,500, we'd then go up to $3,500, and we'd place our point. And then we'd do it for all of the 23 different diamonds, go to the horizontal, go to the vertical, and then place the point. Now, if there are certain points that are of interest for some reason related to your study, you can label some of them. You won't usually want to label all of them, particularly if you have a lot of points. That would start creating way too much clutter. But if there's a few diamonds that are of particular interest, either because they seem different or because they're important to your study, say you're looking at a whole list of countries and Canada, your study's about Canada, but you're comparing it to other countries, then you might want to label, say, Canada on your Scatterplot so that people can see where does it fit in among the other countries, because it's informative to your study. That's optional. It really depends on your study as to whether this is something that would be useful. All right, so using the data in table 7.1, create a scatter diagram to look for a correlation between a diamond's color and price, and comment on the correlation. So pause the video. I'm actually, while you pause the video, I'm going to go back to table 7.1, just in case you want to write stuff down. Pause the video and then unpause it when you think you've got your scatter plot. All right, so we expect, in this case, we expect price to depend on color. So we plot the explanatory variable color on the horizontal axis and the response variable price on the vertical axis. And so this is an example of what it would look like. And if we want to comment on the correlation, so here we'd see that we don't see as strong of a pattern as we saw in our last table when we were dealing with weight, right? There's a much tighter clustering of points into a clear pattern, where here there's much more dispersed. The points, it's harder to see any trend. But if we do look carefully, we can see that there is some level of, as color goes, the number of color goes up, we do see that price seems to go down. There's a lot of variation upwards and downwards, but there does seem to be some type of trend going like this, right? So definitely much more scattered than in figure 7.1, but you may notice a weak trend downwards. And this makes sense because higher numbers of color represent usually a more yellowing of the diamond, where a low number in color would be a more white diamond. And generally, in terms of sale value or desirability or shine of a diamond, a more pure white diamond is more valuable than one that is showing signs of discoloration. But clearly, based on how the points aren't tightly clustered together into a tight correlation, it's clearly not the only thing that matters. All right, so now we're going to talk about types of correlations. And there's three major factors that we're going to look at in terms of types of correlations. So we're going to look at, are they positive, are they negative, and are they linear or non-linear? So first, we're going to look at a series of positive correlation. Are the positive, negative, weak or strong, or linear or non-linear? And we're going to start with looking at positive correlations, positive linear correlations. And so here's three different examples of positive linear correlations. You can ignore the numbers for now. We're going to come back and explain what R equals 0.3, R equals 0.7, and R equals to 1. We're going to explain that later. More, I just want to look at kind of the clustering of the points. Now, in all three cases, we can see a trend upwards, right? As the value of X goes up, the value of Y seems to go up too. And so we'd refer to all of those situations as positive correlations. As one goes up, the other goes up too. But in each of these three graphs, we see differences in strengths of the correlation, right? So in this case, we see that there's a very, very clear relationship here that in this case, even all points fall along a straight line. There's a very, very clear relationship here. In fact, pretty much if you knew the value of X, you could almost perfectly guess the value of Y, right? Because all the points seem to be following in a straight line. So even if I went, here, I could guess that the point would be about here. And I'd have a fairly strong reason for believing that, I might be right, because there's very little, the points are very, very, are clustered into a very tight pattern. Here we see a lot more variation. There's still a very clear upward trajectory, right? So there's still a very clear positive correlation, right? But knowing where a variable falls or where the value falls on X doesn't allow me to predict where it's going to fall on Y quite nearly as accurately, right? So like, for example, if we went to the midpoint on X, right, we've got some points that are all the way down here and some that are all the way up here, right? And so if I found, say, a diamond of this weight, if this were diamond and weight and price, say, if I found a diamond of this weight, I wouldn't have any way of knowing whether it's going to fall here or here, somewhere in between, because there is more variation. But we could still say that there's clearly some pattern here. There appears to be some relationship, or at least they seem to go together. In this case, again, there's still an upward trend. It still seems to go up more or less like this. But it's a lot cloudier, a lot murkier. The points seem to be, just dispersed a lot more, what would appear randomly than in these other two cases. And so if I, for example, found a diamond of a particular weight, and if this were the relationship between diamond weight and price, right, knowing where it is on the X or its weight isn't going to tell me much information about where it is in Y. I could kind of maybe guess that, if it has higher weight, it's going to have a higher price, but I'm going to have still a lot of uncertainty, right? Because there's a lot of points, for example, this diamond is much heavier, but its price is much lower than this one. Again, these ones aren't weight and price. I'm just using that as an example. So there's a lot more variation. Here's an example of negative linear correlations, or three examples. And the real difference between what we saw in the last slide is just that the trend is downward. So negative is showing that as the value on X goes up, the value in Y tends to go down. And so, but much like positive correlations, you can have kind of different strengths of the correlation, right? So over here, we've got the perfect looking negative correlation. From knowing X, you could almost perfectly predict where something will be on Y. There's a very, very, very tight pattern here. Here's kind of more one that's in the middle. It's a strong but not perfect correlation, where we can still, knowing X still allows us to have a pretty good idea of what's happening with Y, but still not perfect. There still is some variability. And here, again, it's still, there's a negative trend that we can identify, but it's a lot more random looking. There's a lot more variability. And so we can kind of get, have a weak idea that as, say, weight goes up, in this case, it would be price goes down, or so we could say color goes up, price goes down. But clearly, we would not be confident in saying that, color is the major predictor or major, if we were trying to, test, does color explain price? I mean, we could have some, maybe there does seem to be a trend here, but it's not particular strong. We would certainly be left thinking that there's also something else that must be going on here. All right, this is an example of no correlation. So while I should just go back one slide. So here we said this is relatively random looking, but we can still see some relationship, right? This just looks like a cloud or a random assortment of points. There's no way of trying to guess what the trend would be. There doesn't appear to be any trend. Drawing a upward line or an increasing line or a decreasing line, or horizontal or vertical line to try to guess a trend. All of them seem equally plausible and implausible all at the same time. There just doesn't seem to be any link that we can identify. And this is an example of a non-linear relationship. And we're not going to deal with as many of these in this course. They exist a lot in reality, but they're more difficult to deal with. And so there definitely is a relationship here, right? We can definitely see, okay, and actually quite a tight and strong looking relationship, but it's not a straight line, right? Normally our positive correlations go up and our negative correlations go down, but this one goes both up and down depending on where it is on the x-axis. So really for the purpose of this course, remember that these relationships exist and that they're possible. And if you're looking at your data and we're using linear models and your linear model tells you nothing's happening, the model's right that nothing's happening in a linear perspective, but that doesn't necessarily mean, say, that your guess of a relationship is wrong. It could be that there's a correlation, but it's non-linear. So just as a recap, we have positive correlations where both variables tend to increase or decrease together. Two variables, negative correlation where two variables tend to change in opposite directions. So if the one on the x-axis increases, the other one decreases. We can have no correlation. There's no apparent linear relationship between the variables, and a nonlinear relationship. The two variables are related, but the relationship results in a scattered diagram that does not follow a straight line pattern. And that could take any number of different shapes. The unifying thing for all nonlinear relationships just is that the relationship isn't a line or can't be fit into a straight line. So how do we measure the strength of correlation? So far we've looked at them in graph and we've said kind of, this one looks strong because the points are tightly clustered together, and this one looks weaker because there's more variation. But that's so far very subjective. Looks strong isn't a really an accurate way of conveying information. And so what we need is a way of measuring correlations. And we use the correlation coefficient, which is represented by the letter R, to represent the strength of a correlation. So the correlation coefficient is a measure of strength of correlation, and its value can range from -1 to 1. So all correlation coefficients will somewhere be between -1 and 1. If there's no correlation, and so the points don't follow any ascending or descending straight line pattern, it's some sort of cloud, the value of R is 0 if there's no correlation. And if it's very, very little, it'll be close to 0. So if you find, you're told that the correlation coefficient is 0, that means there's nothing happening. There's a positive correlation. The correlation coefficient is greater than 0 and less than or equal to 1. So we could see from that both variables are increasing together. A perfect positive correlation in which all the points on the scatter diagram lie on an ascending straight line. So we've seen that, the one where they all fit perfectly into a line. There's a correlation coefficient of 1. So if you see a correlation coefficient of 1, then that means a perfect correlation. Values that are closer to 1 mean strong correlation, and values closer to 0 mean no correlation. So if you think about it, just pretend for now that there's only positive correlations. So 0 means none, 1 means perfect. The closer you get to 0 means weaker, the closer you get to 1 means stronger. Similar logic applies for negative correlations, but this time the range is from -1 to 0. So -1 inclusive and smaller than 0 because 0 means no correlation whatsoever. So when one variable increases, the other decreases. A perfect negative correlation, which again, we saw an example of the one where the example where I said for almost color and price, the one that fit into a near perfect line, or into actually in that case, a perfect line, would be one where there's a perfect negative correlation and R would be equal to -1. Values of R close to -1 mean a strong negative correlation, and a negative values close to 0 mean a weak negative correlation. So if we just think of negative correlation, forgetting about positive correlation, a value close to 0 means weak. A value close to -1 means strong, and a value at -1 means perfect. So, and if then we bring positive and negative correlations together, just think of it as if it's negative, if R is negative, that means it's a negative correlation. If R is positive, it means it's a positive correlation. And the further it gets from 0 means stronger correlation. So size of number or distance from 0 implies the strength. And whether it's negative or positive tells you about whether it's a positive or negative correlation. So if the question on a test is, is this a positive or negative correlation? You would look at first, is it 0? Because if it's 0, it's neither, there's no correlation. And then you'd look at, it's a sign of R positive or negative. And that's everything that you need to know. If the question is it a strong or negative is it a strong or weak correlation? All you'd look at is the distance from 0. Is it close to 0? If so, then it's weak. Is it further from 0? If so, then it's strong. Here's a formula for, or one of the formulas. There's multiple formulas for calculating R. Don't worry, in this class, we're never going to have you, or I'm never going to have you actually do this by hand. It's more just so that you can be looking at what's going on. And so, because of the values that we're seeing, it's taking into account the distance of a point from each point from the mean of X, and the distance of each point from the mean of Y. The division by the standard deviation is to standardize this so that, say one is on one is up to, when we were looking at the caret, right? One of them was, up to, carats can go up to, 24 carats, say, or in diamonds, certainly not even that high. In diamonds, we were up to 3 or 4, I think, in our sample of 23 diamonds. Where price, I think the highest one went up to 15,000. And so automatically the deviations from the mean could seem much larger here than here. And so dividing by the standard deviation just standardizes it. But that's not too important for the understanding it. So what you're seeing is that we're multiplying the distance from here by the distance from the mean here, and then dividing. This is on the surface, actually more intimidating looking formula, but if you ever had to do it by hand, it's an alternative formula that would actually allow you to calculate the correlation coefficient. Its advantage is that it's more user-friendly. This is actually easier to do by hand. The advantage of this one is that it conveys better what's actually going on in calculating the correlation coefficient. It's more evident what this formula is doing. But again, I'm just showing this so that you can take a look and depending on how much you like math, try to understand what's actually going on in the calculation of correlation coefficient. But the only times that we're actually going to calculate correlation coefficients will be in our labs where the statistical software will do the math for you. So that's the only time. You're never going to have to do it by hand or in a calculator. It's too time consuming and not really useful enough. Just try to understand a little bit of what it's about. All right, so how do we interpret correlations, right? So we've seen what they are. We've seen kind of measuring them. And we've seen how to draw a scatter plot. So how can we interpret them? And here I want, in terms of interpreting them, we're going to bring in several cautionary tales. Because there's a lot of things that when we're looking at a correlation coefficient that can lead us to potentially erroneous conclusions. Because there's the correlation coefficient that we calculate can be misleading sometimes. So let's look at this graph of these 10 points here. And if we calculate the correlation coefficient here, we find that there's a relatively high R of 0.880, which is very strong. But if we cover up this point right here, right, and we calculate the correlation coefficient, it's actually 0, right? Because these 9 points, there's no discernible direction, pattern, right? You could draw a line like this, like this, like this, like this, all would make as much sense or as little sense. And so clearly the entirety of this strong, very strong correlation is based on this one point. It's doing everything because when it's looking at it, it's saying, okay, we seem to have this trend like this. Now, potentially that's correct, right? Potentially, if we had more data, this trend, there is a positive correlation and that's right. But this point also could be wrong. This is definitely something that we want to investigate. See, is this a measurement error? Is this just an anomalous case? What's going on with this point? Because it seems clearly different from the other. And more importantly, also for our conclusions, it's having a very, very strong impact on the measurement of the correlation coefficient, right? Because with it, we have a very, very strong correlation. Without this point, we have a very, very weak correlation, where none of these other points, if you removed any of these other points, you would only have minor changes to both of these correlation coefficients. So none of these other points individually has much of a impact on the correlation. This one has a massive impact. And so this is what's called an outlier. So a point that's far away from the others, and they can lead to misleading conclusions. And so it's definitely something you're going to want to watch out for. That's why it's usually good to inspect your data before, say, running correlation and see, do we have any strange points? And then even when you're running correlation, it's always good to graph it to see, are there any points that just stick out that could be problematic to the conclusions I'm drawing. All right, here's an element or an instance where outliers can mask a correlation. So in this previous case, the outlier led us to believing that there's a correlation when there may not be one. Looking at these points, we would have strong reason to believe there's not one. So we definitely want to be suspicious that in reality, maybe there isn't one. In this case, the outliers, these 2 points, are leading us to a conclusion that there's a weak correlation when there may actually be quite a strong one. So this is a graph looking at cycling, number of hours that somebody cycles per day and the amount of calories that they consume. And if we look at this entire graph and we calculate the correlation coefficient, we see a relatively weak one of 0.374. So a positive one, but it's not particularly strong. Now, if we look though at these 2 points, and what happens if we remove them, right? If we remove these 2 points, the ones that, down here and over here that just seem very different from everything else, we end up with a line like this, which isn't a perfect correlation, but it's a very, very, very strong looking correlation. So it seems to potentially be this raises questions for us, right? Moving forward, what's going on with those points? Now, we don't want to toss them out, right? Because they may still be good data. It's not necessarily measurement error, right? And so if we were to eliminate them, we would then come to the opposite conclusion that this is stronger than it potentially should be, that clearly there are people that will act differently than what this line suggests. But we would certainly also want to be investigating what's going on with those 2 points. Are they measurement errors? Is there some other reason that they're either so low or so strong or so high that's not being covered or not being explained here? Is there some other factor that we need to be? So this is an area where you'd want to be cautious. So again, you'd want to be inspecting and you'd want to look at those points and try to see, all right, who was that? What's going on? And if it is a measurement error, then potentially drop them. But if you do drop them, again, always report the reason, just for full disclosure to your reader anytime that you eliminate data, and really that you should keep that to a minimum, and always explain the reasons for doing so. Now another example of where you need to be careful when you're dealing with correlations is in terms of inappropriate grouping. So here we have hours of TV watched per week and grade point average for different students. And so it's a hypothetical study, and this is the clustering of data that you get. So they collect 21 data pairs, and the diagram shows virtually no correlation. So we have a very, very, very weak negative correlation of 0.063. So really near zero, which is so apparent conclusion is that TV viewing habits are unrelated to academic achievement. And if we just run on the number, it would seem to support it. But if we look a little bit closer at this data, it appears that actually, rather than just nothing happening, this would make it seem like there's almost just like a cloud of points, no discernible pattern. But if we look at this, actually, we kind of do see patterns. We kind of see one like this and one like this. And so this can raise questions about, are these grouped together inappropriately? Is there something else, other variable that needs to be taken into account too? And maybe these are people who are part of different groups. So one astute researcher realizes that some of the students watched mostly educational programs, while others tended to watch comedies, dramas, and movies. So she divided the data into 2 groups and then looked at the impact of television on GPA. So group 1 watched educational programs. So here's the amount of TV they watched and their GPA. And here's those who watched regular TV, then hours per week and GPA. So separate them out into 2 different groups. And in this case, then we have much different conclusions, right? A strong positive correlation for students who watch educational programs. So increasing number of hours leads to increased GPA. And then for the students who watched non-educational programming, we see a very, very strong negative correlation. And so weekly hours of TV, as it increases, it leads to a decrease in GPA. And again, this is fictional data, but it's more just to demonstrate that, you've got to be careful. Is your data grouped properly? Should they all be together, or should they potentially be separated into more than one group? Here's another example of inappropriate grouping. So this is a study looking at car weights and car price. And if we look at it, if we look at it as a whole, we see a very strong positive correlation, right? we see a pattern kind of going up like this. All of the low weight cars also have a low price. All of the high weight cars also have a high price. But the thing that should make you a little suspicious here is that there seems to be nothing in between. And so it's, fair to ask what's going on maybe within each of these different clusters. And if we look at inside each of these clusters, we see almost no relationships whatsoever, right? There doesn't seem to be any real pattern here. There doesn't seem to be any real pattern here. So what might be going on? Well, what possibly could be going on is that these are, say, compact cars and these are trucks. And it's not that weight has any impact on price. It's that trucks are more expensive than compact cars. And so all the trucks are up here because they're heavier, and so they're more expensive. And all of the compact cars, which are lighter, are down here. But if we look within each of the different categories, if we look at trucks, weight doesn't seem to have an impact on price. And if we look at compact cars, weight doesn't seem to have an impact on price. And so what this would suggest is that we would want to be making separate graphs for both trucks and compact cars because it's misleading in terms of look at the correlation, because these aren't groups that should be compared for this. An important, one of the most important things I want you to remember out of this entire presentation is that correlation does not imply causation. So just because you see a really strong correlation, that doesn't mean that the value you've got on the x-axis is causing the y-axis. There's other things that are needed in order to establish causation. So you can find a nearly perfect correlation, and the two things may not be correlated at all. And there's a few possible explanations for this. One, it could just be coincidence. Even things that seem perfectly correlated, and you can draw an almost perfect graph. Sometimes it just happens because there's all kinds of coincidences that occur in nature. And we'll take a look at a couple of them or a few of them in the next slides, where you see very strong looking correlations, and it's nonsensical to say that there's any level of causation between them. It could be that both correlation variables might be directly influenced by some common underlying cause. So it might not be that the variable on the x-axis is explaining the value or the variable on the y-axis. It may be that some other variable, z, is explaining both the value of x and y. So it's not that x is causing y, it's that z is causing both x and y. And also, even if it is the case that the explanatory variable, the one we place on the x-axis or the horizontal axis, actually is a cause of the variable that we place on the y-axis, or the vertical one, it doesn't mean that it's the only cause. And particularly when we're dealing with weaker correlations, like when we talked about the color of a diamond and its price, right? We did see a weak negative correlation, but even at the time I had said, just based on how spread out it was, that we'd think that there's got to be something else going on too, right? That by itself doesn't seem to be enough to explain. So it may be the case that what we see when we find our correlation, that we've identified a cause, but it may be one of several causes. So that doesn't mean that we found the end of the story. And so that's really important to remember, that finding correlation is an important step in establishing causation. It's definitely one of the steps that we want to be looking at, or one of the things that we want to be looking at, but it's not enough by itself. So here's some examples of, to try to show you that correlation doesn't necessarily mean causation. So here's the first graph of one where things seem to go together, but we couldn't in any way say that we would expect a causation, right? So these two lines seem to follow each other remarkably over time. But the red line is the number of people who drowned by falling into a pool. And the black line is the number of films that Nicolas Cage appeared in. I can't think of any possible correlation for how the number of films that Nicolas Cage appears in is either caused by or causes people to drown by falling into a pool. Um, Here's number of people drowned after falling out of a fishing boat and the marriage rate in Kentucky. Um, Again, so not perfect correlation, but these fit together quite nicely. Divorce rate in Maine and the per capita consumption of margarine. These ones actually fit together really nicely, including even this downward bump here. But we certainly couldn't make a claim that these two, there's a causal relationship between any of these, right? This just comes down to, pure coincidence. Letters in the winning word of Scripps National Spelling Bee, and number of people killed by venomous spiders. Again, no real relationship here or no relationship of any sort that, I couldn't really come up with a story as to how these are related. But if we look at the graphs and, without telling you what these were, and I ask you, is there a relationship here? Would obviously say, yeah, there does appear to be some form of relationship here. And there would be a strong correlation just looking at this graph, but there's not a causal relationship. All right, so best fit lines and predictions. So far when we've looked at our graphs, we've said, I've kind of drawn lines saying, it looks like the trend's like this, or it looks like the trend's like this. But oftentimes we actually fit a line, and this line allows us to try to make predictions for, additional points. If we've got weight and price, so weight of diamonds and price of diamonds, and we've got, a line like this, then if I find an additional diamond, if I know its weight, I can then make a prediction for its price. So the best fit line, also referred to as a regression line on a scattered diagram, is a line that lies closer to the data points than any other possible line according to a standard statistical measure of closeness. So we don't just randomly draw a line, there's actually statistical methods for choosing the line. Now, there's a few cautions before we go any further and kind of explain how best fit lines are drawn. So don't expect the best fit line to give a good prediction unless the correlation is strong and there are many data points. If the sample points lie very close to the best fit line, correlation is very strong and the prediction is more likely to be accurate. If the sample points lie far away from the best fit line by a substantial amount, the correlation is weak and predictions tend to be far less accurate. So that kind of goes along with what we talked about earlier, right? When we saw kind of the points in a perfect correlation in a straight line, well, you could just, forget about even fitting a line to it. You could kind of just, by looking at it, see, okay, I'd be fairly confident in predicting an additional point because there's a very clear type pattern. Where when we looked at those weaker correlations, right, yes, there seemed to be a pattern, but there's tremendous variation. So even, if I found two diamonds that had that were 1 carat in weight, there's a wide range in what the price could be. And so the stronger the correlation, the more confident we would be that our prediction is good. The weaker the correlation, the less likely we should be confident that our prediction will be good. So we could still, the prediction line in either case is our best guess as to what the value would be, at least using these methods. There could be other methods for getting better guesses, but this would be our best normal guess for what it would be, but how accurate it'll be or how confident we can be will depend on the strength of correlation. Don't use a best fit line to make predictions beyond the bounds of data points to which the line was fit, right? So if, for example, if we had diamonds that were 1 to 3 carats or 0 to 3 carats, and we and so had the price. That doesn't mean, and we fit a line to that. That doesn't mean that we could use that line to make a prediction about what the price will be of a 6 or 7 carat diamond, because we have no reason to know whether that correlation fits there. We could only be confident in kind of the range where we've seen data, because it may be that something different kicks in, another factor becomes more important at that weight. It could be, and sometimes it'll be that even weight of that is nonsensical, and so the prediction that you'd make would be, if you got, for example, if you extended out your caret far enough, your weight far enough, and went to 1,000 caret one, which I mean is theoretically possible. I mean, you could, even if not realistic, right? The price, if we just drew out that line, may be so astronomically high that no one's going to pay $10 trillion for a diamond. But eventually, eventually that line would hit 10 trillion if you found a heavy enough diamond. But at a certain point, the price just becomes that it's not possible. So you have to be careful about what predictions you make and keep it within bounds of what your data allows. A best fit line based on past data is not necessarily valid now and might not result in valid predictions of the future. Now, it may be our best guess for now or for the future, but it's not necessarily the case that something that's a trend that we've seen in the past will continue, because so many factors can change as we go along. And so there's many times that we've seen trends that change through time. So again, that's a case of taking data outside of the bounds, the range. And so that's something to be very careful about. Don't make predictions about a population that's different from the population for which the sample were drawn. So you can think of that in terms of like our car example, where if you've done something looking at the weight and found the correlation, weight of a compact car, and found a correlation with price, that doesn't mean that you can take that correlation and assume that it'll fit for other types of cars, for trucks, for SUVs, for luxury sports cars. You've got to be careful about moving to different populations. And remember that the best fit line is meaningless when there's no significant correlation or when the relationship is nonlinear. You can technically fit a correlation line to correlations that are near zero, or to many non-linear relationships, but it's going to be fairly meaningless. So if you've got for example, points that are kind of arranged in a non-linear like this, you could fit a line that went like that. And if you use the best fit line techniques, that's what you would end up getting. But it's pretty much a straight horizontal line is pretty much meaningless in explaining a data set that goes up like this and then down like that. That doesn't really help you understand or predict what's going on. All right, so here's an example. So you found a best fit line for a correlation between the number of the number of hours per day that people exercise and the number of calories they consume each day. So we looked at this with cycling. And you've used this correlation to predict that a person who exercises 18 hours per day would consume 15,000 calories per day. And is this a valid prediction? So pause the video, think about it for for a minute, and then unpause, and let's see if what you found fits with the right answer. All right, so the solution is that no, this would not be a valid prediction. And why? So because we're taking the data outside of the bounds. And in this case, we have a lot of reasons to be suspicious that this wouldn't work. And the main reason is that no one actually exercises 18 hours per day on an ongoing basis, right? So this, there could be different physiological things that happen in terms of the amount of calories at that point, but it's also just nonsensical to say that someone exercises 18 hours per day. And so any predictions based on models, we would have very little reason to, conclude that the amount of calories you consume after 2 hours of exercise or 3 hours of exercise or 4 hours of exercise has anything to do with what would happen if someone were forced into 18 hours per day, if assuming that were even possible. So we couldn't trust any predictions based on kind of extending the data set out to 18 hours per day. So how do we find the best fit line? So first, let's just kind of recall how lines work when in terms of graphs. You may recall that the equation of a straight line can be written in the general form y is equal to mx plus b. So your intercept and your slope, and then your x value and your y value, where m is the slope of the line and b is the y-intercept of the line. Now for the best fit line, we typically write, so we kind of just repurpose this. So y hat is equal to beta naught plus beta 1 times x. So your beta naught is your y-intercept, so it's replacing the b here. Your b1 or beta 1 is your slope. X is still your value of x on the x-axis. And y hat is the predicted value of y. Predicted because we actually have a true value of y, but we're making a line for the predicted value. Now, in general, like we said, other than when there's a perfect correlation, there's always going to be some difference between our predicted value and the true value of y. So again, think of any of the different graphs that we've looked at where there's a correlation that wasn't perfect. There's always a little bit of variation for any value of x. There's a little bit of variation in terms of y. And so when we fit a line to that, there's going to be some different distance between where the point on the line is for that value of x and where the true data points are, the true values of y. And so we can measure this error in our predictions with the formula R, and so this isn't the correlation coefficient. It's unfortunate how many R's there are in today's lecture. So R sub I, so R sub I just means for every data point. So if we had 23 diamonds, we'd have R1 through 23 is equal to the true value minus the predicted value of I. And we refer to this version of R as a residual. So it's kind of what's left unexplained or unpredicted by our best fit line. So our best fit line is saying this is our prediction, this is kind of our error. And so we would calculate this for each point. So we'd have an R1 through 23 based on what is the prediction, or what is the true value of 1 through 23, and what is the predicted value of 1 through 23. So we'll look at a few examples. So imagine that we've got, in reality, we have 2 points, right? And we can ignore for now what the values of x are, because the residuals are purely based on our predicted value of y and the true value of y. So let's think if there's 2 points. That should be a y1. So y1 is equal to 5 and y2 is equal to 10. So in reality, this is what they are. Based on our prediction, we have predicted for 1, and that I should be a 1, is equal to 7, and predicted for 2 is equal to 7. So we could find then the residuals for both of those. And so remember, residual for each point is the true value minus the predicted value. So for the first point, so for the one where it truly is 5, but we predict 7, we have a residual of -2. And for the second point, where it truly is 10, so it could be $10,000 if it were diamond or whatever, and price of diamond, and we predict 7, so there's a residual of 3. So there's a distance of 3 between our predicted value. So our predicted value was 3 below the true, And in this case, our predicted value was 2 higher than the true. And so it's showing the size of our residual. We could do another example. So in reality, we've got 0.1 has 5, and in reality, 0.2 has a value of 10. But we predict that 0.1 has a value of 6 and 0.2 has a value of 9. And so if we calculate the residuals, we'd find a residual 1 of true value minus expected value minus 1, because the predicted value was 1 above the true value. And residual 2, 10 minus 9 is equal to 1, because the true value was 1 above the predicted value. Yeah. All right. So that's kind of the concept of residual. So for each point, we can calculate how far the predicted line is from the true line. And this could be really important, the concept of residual, for how we calculate what the line will be. So if we draw a line on a scatter diagram, we can measure the vertical distance between each data point and that line. The best fit line most commonly used, the least squares model, fits a line that minimizes the sum of the squared vertical distance. To change to what we looked at the last slide, it fits a line that minimizes the sum of the squared residuals. A large sum means that the vertical distance of data points from the line are fairly large, and hence the line is not a very good fit. A small sum means the data points lie close to the line and it's a good fit. Of all the possible lines, the best fit line is the line that minimizes the sum of all. So it's just kind of repeating kind of conclusion. All right, so here's an example, because this may seem confusing just in terms of text. So I'm going to show you some examples for how different lines would have different sizes of residuals. So here's the example that we looked at before, which is the Y2 went a little crazy for some reason, but it's all right. Somehow getting subscripts. Okay, so here's the Y1 that we had right before and the Y2 that we had before. The subscripting seems to have gone weird on full screen, but that's all right. Yeah, so this is, we had before, right, the true value was 5 and the true value was 10. And then that first line, or the first predictions that we made, was that the true value for 0.1 was 7, and the true value of 0.2 was 7, right? And that was based on, we tried fitting this straight line, right? We just looked at the points and said, hey, let's try a straight line to see if how well that explains it. And so here we've got, this size of residual, right? So our predicted value is this far. So the vertical distance between them, or the size of the residual, and calculate the residual in the same way we did before. And here is the distance between the true value and the predicted value, or the residual for 0.2, and it's quite big. Now let's think about the line that would go with that second predictions that we had. So remember, the second one we predicted that it would be 0.1 would be 6 and 0.2 would be 9. And so here we see that, in 0.1, or for 0.1, our prediction's much closer. This line is much closer to the true point. And in this case, the line is much closer to the true point. Give me 1 second. And clearly, when we look at these two lines, we see that the blue line seems to fit better, right? It may not be the best line, but it's closer than with the red line. We'd be more confident with this line predicting because it's closer to the point. And so the concept of the least squares is finding line, and normally there's more than 2 points. With 2 points, it's you could actually fit a perfect line, but normally we're not dealing with data sets with 2. The idea is finding the line that for all of the different points along the way has the smallest sum of the different squared residuals. So we take this residual, we'd square it. We take this residual, we'd square it. Say we had another point here. We take this residual, we'd square it. We take this residual, we'd square it. If we had a point over here. And we take the line that we're looking at all the different points has the smallest sum of squared residuals. Let's look at calculating it. So in reality, again, so 0.1 is 5, 0.2 is 10. And before we had found that for the prediction where both were 7, we had a residual of -2 and we had a residual of 3. So if we take the sum of squares, so that really just means sum of squares. So we square each value, we square each residual, and we add them up. So in this case, we have 2 points. We had a residual of -2, we square it. We had a residual of 3, we square it, and we add them up. And so 4 plus 9 is equal to 13. So we have a sum of squares of 13. In this case, we had a prediction of 6 and 9. We had residuals of -1 and 1. So this is what we had calculated earlier. Sum of squares, so we square each point. So -1 squared, 1 squared, and we add them up. 1 plus 1 is equal to 2. And so the blue line has a smaller sum of squares. So in terms of evaluating from at least in terms of selecting, the best fit line, the blue line would be better than the red line. And when we end up selecting a line, we would select the line that has the smallest number here. So this isn't something that you do by hand, but the statistical software would look at all of the different possible lines that you could find, and it would select the one that has the smallest number here. And so it could go through, thousands of different line combinations and, take the one that is best. So why do we square? So there's 2 reasons that we square. There's 2 things that squaring does. Because, you could say, why don't we just add up the residuals? This one's -2, this one's 3. And the reason that we don't just add up the residuals is because some of the points are too low and some of the points are too high, right? So this one, could be too low and this one could be too high. And what you end up having is a situation where, these could cancel each other out. So for example, if you added these up without squaring, you'd end up with a residual of 0. If you added these up, you would end up with a residual of 1. But this could lead to some problems, right? You could have, for example, imagine again 2 points again, and one has a residual of -5, and one has a residual of +5. And if we didn't square it and we added them up, we would come up with a sum of 0. And so that would seem to imply perfect prediction. But really, we'd miss by 5 on each. And I consider another set of predictions, where on the first one, we have a residual of 0.5. On the other one, we have a residual of 0.5. We add them up, we get to a sum of 1. And based clearly, if you have one where if you've got a set of predictions where in both of them you miss by 0.5, and another one where you miss both times by 5, the one where you miss by 0.5 is a better predictor. But because the one where they both missed by 5, one missed high and one missed low, if you just sum them, they cancel each other out. And so you need some way of dealing with this cancellation out. Now, and squaring does that, right? Because if you square a negative number, you end up with a positive number. You could also do this with absolute value. So one possible solution would have been to just sum the absolute value of the residuals. So absolute value of 2, absolute value of 3, absolute value of -1, absolute value of 1, and sum those. And that would get rid of that problem. That would, you then for the ones that both missed by 5, you would end up at 10, and the ones that both missed by 0.5, you'd end up 1. And so that would fit better. So there's a second thing that squaring is doing. it's also penalizing values for being further. So the bigger distance you are, the more you're going to go up. So for example, 2 squared is 4, 4 squared is 16. So, 5 squared is 25, 10 squared is 100, jumps much further. And so by squaring, you're giving a bigger penalty to bigger misses. And so that's a choice that was made in selecting sum of squares, that we want in terms of selecting the best fit line, that points that are far off that have big residuals are going to have a really big impact on the sum of squares. And points that are closer to the line are going to have a lesser impact. And so it's going to be a exponential relationship based on distance, not just a linear relationship based on distance. And so that was a choice that was made. So that's the second thing that squaring does. So one is to penalize more for greater distance, but the other point, which could have been done with absolute value, is to deal with the problem of some points are too low and some points are too high. All right, so correlation coefficient and best fit line. So the square of the correlation coefficient, or r squared, so the square of r, is the proportion of variation in a variable that is accounted for by the best fit line. So if you've got big deviations from, if you've got big residuals, then there's a lot of variation in the variable that's not accounted for by the best fit line, right? Because the best fit line is saying that your prediction is all along this line. In reality, there's a lot of extra variation. If all the points are tightly clustered around your line, then that means that that line is accounting for the correlation is accounting for most of the variation. So think of the ones where you've got a near perfect correlation. You can almost perfectly predict where y will be based on knowing x. And so there's very little additional unexplained variation. And so that would lead to a high value of r squared. Still, maximum being 1. The range for r squared would be 0 to 1. Again, because your negative correlations when squared would go to a positive. Now, if you've got large residuals, yes, you've got your prediction, and that's explaining some, because there's some correlation, but there's a lot of additional variation in the explained variable in y that's left unexplained. And so that will result in a small value of r squared. So here's an example. So political scientists are interested in knowing what factors affect voter turnout in elections. One such factor is the unemployment rate. Data collected in presidential election years since 1964 show a very weak negative correlation between voter turnout and the unemployment rate, with a correlation coefficient of r is equal to negative 0.1. Based on this correlation, should we use unemployment rate to predict voter turnout in the next presidential election? So pause the video, think through this problem, and once you think you've got an answer, unpause and we'll take a look at it. All right, so here's the solution. So the square of the correlation coefficient is r squared. And the square of negative 0.1 is equal to 0.01. And if we interpret this, remember that r squared is the amount of variation in y that is explained. And so this would mean that only about 1%, because 0.01 would lead to 1%, of the variation in the data is accounted for by the best fit line. Nearly all of the variation in the data must therefore be explained by other factors. We conclude that unemployment is not a reliable predictor of voter turnout. Only 1%, I mean, that's still something. It still has an impact, but it's a very weak correlation and explains therefore very little in the variation, right? So we still might have, a negative correlation line that goes, but if you look at the points, they would all be very distant from that line. They'd be clustered very, very distant. There wouldn't be a very visible pattern. And so we would not be confident in guessing, what will voter turnout be based on knowing the unemployment rate or based on whether someone's employed or not. We wouldn't really be very confident in guessing. There's some other factors. So again, when we talked about correlation does not mean causation. In this case, there could be some level of causation, but it's one of many, many, many factors. And based on looking at this, it doesn't seem to be one of the important factors. So far we've looked at, one predictor and one outcome variable. But sometimes we want to look at, especially when we're talking about, there's more than one possible explanation. We want to fit a model that looks at, do these 2, 3, 400 things predict, say, the price? And so we use multiple regression, allows the calculation of a best fit equation. So because we're dealing with multiple variables and so multiple axes, it's no longer really a line, but a best fit equation that represents best fit between one variable, such as price, and a combination of 2 or more other variables. So if we want to explain the price of diamond, and we'd be doing so based on, say, weight and color. And the coefficient of determination, so capital R squared, tells us the proportion of the scatter in the data. So the proportion of the scatter in price accounted for by the best fit equation. And the equation then would have kind of a slope for based on weight, a slope based on color, a slope based on whatever other variables, and so we still have your kind of y predicted is equal to beta naught plus, say, beta 1 for weight, and beta 2 for color, and beta 3 for clarity, and whatever else. This isn't something you're going to be calculating manually. Potentially in a lab we'll deal with it, but this is something that if you run a regression model in a lab, this will be one of the outputs if it's a multiple regression. But best fit lines and coefficient of determination are stuff that you're never going to have to calculate by hand. All right, that concludes the lecture on correlation, and I hope that you have a really good day.